14, how the masses of the three main types of nuclear radiation compare. We had this on a checkpoint. We have alpha, which is our 4/2 helium, beta, which is our 0/1 heat, or you could write the beta, and gamma, which is gamma. Those are three most common. And what can you tell me about them? In terms of mass, how are they ranked right now? Heaviest to lightest, because it's not even mass. How about penetrating ability? Least to most. How about relative amounts of energy? Least to most in general. Okay, so this question will be asked you about that. And it would be really helpful to listen to the alpha, beta, gamma radiation song, because the answers from the course will get stuck in your head, and then you'll do awesome on this question. Okay. Which of those processes, well, which of all five processes? Because we also have our positron and our K capture, and we have neutron bombardment. Which of those does not reduce the atomic number of the nuclide? Which of those does not reduce the atomic number? Gamma radiation does not. Capturing an electron is going to do what to the atomic number? Raise it by 1, right? What else? Neutron bombardment, well, depends on what, it depends on if that nucleus can take in that neutron and not decay, or is it going to break into daughter? So, what does beta do? What does beta do to the atomic number of the nuclide? Increases it by 1. Okay. Alrighty. 16, the specific symbol for a beta particle. The question says, which of the following is a nuclear symbol for a beta particle? Which of the following is the symbol for a beta particle? Gosh, this is so easy. Right.
Capture.
Alrighty. 17, how do the half-lives of different radioactive isotopes compare? Do all isotopes have the same half-life?
No.
No. What do you know about the ones that are furthest from the belt of the stability? Shorter half-lives, because they're least stable, and the ones closer to the belt of stability tend to have longer half-lives. Okay? But it's not like every radioactive isotope does not have the same half-life. They all have something special. Number 18, you'll be given a half-life problem. You will have the starting and ending mass and how long it was reacting. Okay? So what if we did something like this?
So it was like the problem
we have 250 grams of a nuclide out of an original 500 gram sample. And the time that this has gone on has been 10 years. How do we use that to figure out the half-life of this particular isotope? Yep.
Oh.
Do you know? Do you know?
Yeah. You divide 500 by 2 until you get to the original number.
Okay, you have 500 divided in half until you get to 250, which is how many half-lives?
1.
1. And it took 10 years for that to happen, so
Half-life is 10 years.
the half-life is 10 years.
I don't know why I said that, I'm sorry.
Okay? What if this was 125?
20 years. You had 2 half-lives.
That would be 2 half-lives
5 years.
in a 10-year period. So each half-life is 5 years, not 20, 5 years. Okay? It'll be a problem that's that easy. Number 19 is very similar. You're going to get a table that lists several nuclides and it tells you their half-life. And it is going to ask you about, it's going to ask you the same thing in a percentage. So instead of saying we're going from 500 grams to 125, what if it said we went to 25% of the original sample? That would be 2 half-lives. So you can think of it that way, right? Or if we went to 12.5%, it would have been 3 half-lives, and so on. So same idea. And then you just multiply by half-life. Yay, 2 pages down. No, 3 pages down. Number 20, what the 3 specific parent nuclides are. The common parent nuclides. You saw them in decay series. One of them is uranium-238. What is another one?
What? Radon.
Of the parent nuclide? No. Common in the decay series. Who looked at the decay series pictures on Moodle?
Oh, really? Something with a B.
Who looked at the one in the simulation? Uranium what?
239.
235.
Oh,
Okay. And there's a thorium. Do we know that one?
233.
232. I think you've got some problems on your worksheets with this. Okay? What is an element that's definitely not going to be a parent nuclide? Nitrogen, yes, and lead. Why lead?
Because that's the product.
Because that's what they're decaying into. Okay. A decay series starts with what? What are these called?
Radioactive isotopes.
Parent nuclides. Yeah, this is the easy question. Parent nuclides, and they end up being daughter nuclides. 22. What is required in order to do artificial transmutation? To artificially cause a nucleus to change, what is required?
Radiation?
Could be neutron bombardment, so we need some particle, and what else? Yeah, closed container. They tend to do this in what very large pieces of equipment? What? Then the Large Hadron Collider, a particle accelerator. And how much energy does that take?
A lot.
A lot. A lot. Okay. What number are we in? 23? Those were all the answer.
Oh.
How artificial radioactive isotopes can be prepared. Okay? What can we shoot at small things to make other things? Neutrons and other small things and maybe positrons, alpha particles, other small nuclei. Okay. 24. How do magnetic fields affect the common types of radiation?